In the previous example, we saw a Jack program that processed what can be called an atomic object. A fraction is something that need not be divided into, split into smaller atoms. So a fraction is a fraction is a fraction. However, we can also use object-oriented programming in order to manipulate and create objects which are collections of atoms, so to speak. And the most generic collection of these is called list, which is a very important abstraction in both theoretical and applied computer science. So we'll spend a whole unit talking about list processing. So what is a list? A list essentially is the atom null, which can be thought of as the empty set, or it's an atom followed by a list. And we use this notation in order to represent lists. So here's an example of several lists, the empty list, and then 5 followed by the empty list, then 3 followed by 5, followed by empty list, and so on and so forth. It's kind of painful to write all these parentheses, so instead we use abbreviated notation to describe lists. These are agreed upon notations, but back in our mind we remember that we actually refer to creatures that each one of which consists of an atom followed by a list. So this is a highly recursive data structure. And the atoms can be anything. They can be integers, as we have in the example here. They can be strings, they can be arrays, they can be other objects, they can be lists in themselves, and so on and so forth. Now, programmers tend to think about a list as using this metaphor here. So once again, this is a collection of atoms that are linked together. That's why it's called a linked list sometimes. And notice, however, that this whole thing is one object, right? It's one object. And in this example here, we have a pointer variable, v, that points to this object. And the question, of course, is how do we create and manipulate such collection objects? All right, so that's what we'll do in this unit. And here is an abstraction of, or an API of a class designed to manipulate lists. So we see that we have a constructor for creating the list. And we use the terms car and kuder for historical reasons to describe the atom and the tail of the list, which is a list in its own right. And then we have a print method that goes through the list and prints every one of the atoms. And we have a dispose method that recycles all the memory resources held by the list, which may be a gigantic pile of memory, because this list may well contain 1 million such atoms. And so when we don't need this list anymore, it makes sense to recycle its resources. All right, now obviously in reality you may want to add more functionality to this abstraction, because the whole beauty of a list is that you can insert atoms in the middle of the list as you please, or you can delete atoms from the middle or the beginning or at the end, or you can insert a list into a list, or you can pursue it from beginning to end or from end to beginning. There are many different things that you may want to do with the list, but all of them don't belong to the NAND to Tetris course. So once again, this is not a course about list processing. Also, there are excellent languages to do it, like Lisp and Scheme, and yet in this course we will do it in Jack. All right, so here we have the list abstraction, and here we have some client code that seeks to create a list, the list 235, and manipulate it. I will show you the code without discussing it, because in the next slides I'm going to spend a few minutes discussing every line that I now go to present. So at the beginning, we have 4 lines of code that together create the list that you see in this diagram. Then we print the list, and when we'll do it, we'll see the output 235 on the screen. And finally, we dispose the list and return. So this is the client code that demonstrates the three sort of quintessential things that we want to do with the list, which is creating it, processing it, in this case, printing every item in the list, and finally, disposing it. And once again, there are many other things that you may want to do, but believe me, all of them are derivatives of these three operations, as we now go to explain. So let's start with create. Here's the client code, which is identical to what we had before. And we see that it includes three calls to the list constructor, right? So let us open the black box and see how we can write a list class. And the first thing, as usual, is to ask ourselves, what kind of data does the list feature? Well, a list consists of an atom or some piece of data and a list, right? So let's define two fields that represent exactly this information. A data field of type int, because we decided to create a linked list of integers, and the next item in the list is a list. So we have a next pointer of type list to point at the tail. And here is our constructor called new. And the constructor asks, we don't see it, right? But the constructor asks the memory system, the operating system, to come up with enough memory to represent this two-word block, car and kuder, or data and next. And then it returns the address of this block, as all constructors do. And that's it. Okay? So let us see how this code actually runs. And this will give us a lot of insight on how to build a list and later on represent it in memory. So it all starts by creating a v pointer. So, we'll get a variable that contains something. Because you implemented the VM language, you know that it will contain 0, because if this is a local variable, all local variables are initialized to 0. So this variable does not know it yet, but it's going to be a pointer. Right now, it contains the value 0. And then we invoke the list constructor, and the list constructor is going to come back with a block of memory that represents the number 5 and null. And notice that we use this terminator icon to describe null. And v is going to point to the base address of the object that was returned by the constructor. Essentially, we say v equals this, if you think about it, because this was the return value of the constructor. And then the next command, if you think about it for a few seconds, will accomplish this thing. And by now, the previous version of v is no longer relevant. And so the next command will do exactly the same, and the previous value of v is irrelevant, and that's the end of the story. Now, in closing, I'd like to point out that this list construction code can also be done using this somewhat shorter logic. And in general, by the way, this is just one way to construct a list, right? I could have written additional constructors that make the list construction much easier. For example, I could have offered a constructor that takes an array and creates the list from the array. It's all up to the person who designs the API and implements it later. Or, up to the person who hires us to develop this abstraction. All right, so we saw how to construct a list. The next thing that I want to illustrate is how we march through a list and how we do it what sometimes is called sequential processing of a list. So I will illustrate the sequential processing using a print method. And when we run this method, we expect to see the contents of the list on the screen, as we saw before. And here is the body of the method. Once again, don't worry about the code. Don't even read it, because I'm going to simulate the code, and everything will become clear during the simulation. So here's the client code that calls the print method, but it begins from building the list. So once the list is built, we're going to have this abstraction that we saw before. And now the client code calls the print method on the V object. Now, in object-based programming, people don't always know it, but once you will write the compiler in the next module, you will know it very well. When you call a method on an object, you are implicitly passing the object as a parameter to this method. So when we do v.print, we pass v to the print method. And once the print method starts working, it doesn't know what v is, right? V is an identifier that exists outside the world of list. It is not defined in the list class. Instead, we have a very special variable called this, which stands for the current object. So now this is the point from which we are going to refer to the object that was passed to it. So as we see in the diagram, now the entry point of the list is this. And then the code goes on to create another pointer of type list called current, and it sets current to this. So we get this situation here, 2 pointers referring to the head of the list. And now we enter this loop in which we ask repetitively, or we do, as long as current is not null, we want to print the current atom and move forward. So we print the value of this atom, which is 2. Then we print a space, and we move current to the next head of the tail of the list. Once again, we see that it's not null, so we print 3, and then we move it forward. It is still not null, so we print 5. We move it forward, and finally, current equals null, in which case we get out of the loop, and we find a return. We return to the calling code. Once we return to the calling code, of course, all the stuff of the print method is going to be recycled, so this and current no longer exist, and once again, V is being reinstated and points to the list as we had before. So I guess there are 2 comments which are in order here. First of all, notice that the print method is quite invasive, if you will. It goes into the list and it goes through every item along the list, and there's a lot of drama going on, and yet, as far as the client is concerned, the client only asks to print the list, and once this thing is done, the list comes back to the client, so to speak. It never left him, and he can go on and do whatever he wants with it. So this, once again, is this beauty of the abstraction versus the implementation interplay. The abstraction is trivial. The implementation is not trivial at all. But the client doesn't care. And the second comment that I'd like to make is that the printing here is not terribly important. The printing is just a sort of a placeholder to describe methods that, once again, go through every item in a list and do something to all these items. So I could have written a very similar method that, for instance, goes through the list and increases every value by 10% or something like this. So this is sort of an example of numerous processing algorithms, not algorithm or methods that could be very useful in the context of lists. All right. The last thing that I want to illustrate about lists is what I call the recursive access. And we'll do it using the dispose method as an example. And the purpose of dispose is to take this list and recycle every one of its items. Here's the code that does it. No need to read the code. We'll do it in a minute. I just want to point out that it's a recursive method because the dispose method basically disposes the tail of the current list. And the client, as usual, creates the list, gets this abstraction, and then the client says dispose. Once again, when we say dispose, control moves to the dispose method. The dispose method does not know what v is, and instead now the variable this points at the object that was passed to dispose. And next we see that we have this if expression that says as long as next is not null, do something. Now what is next? Next is the field of the current object, right? Well, next of the current object is not null, so we have to do dispose. But the dispose now is applied to the tail of the list, which is represented by next. So now this, when we get into this level of the recursion, this now points at the tail of the list. Once again, it's not null. So once again, we call ourselves, we call dispose. Now this points at the last item in the list, and indeed now next is null. And because next is null, we're going to move to the base case of the recursion. And we find here our acquaintance dalloc. We've seen it before. And dalloc knows how to take an address in memory and recycle the block which begins in this address, the memory block which was previously assigned to represent the current object. So once dalloc ends its work, this item is going to be recycled, and we are going to return. Now we are going to return precisely to the position where we have to do another dalloc. So we recycle this part of the list also, and we do a return. We recycle that item, and we do a return. And once we do this return, we get completely out of this recursive method. And what used to be called this goes back to be named v. But now v points to nothing, because we basically disposed everything in this list, so the list is no more. This has been an example of recursive processing of lists. It is very natural to process lists using recursion, because the list is a recursive data structure in its own right. And here we have sort of a very clean example of tail recursion, literally speaking. And yet, don't forget that recursion is a very inefficient operation. And if you had tried to do that with a big list, you may have gotten Stack Overflow. So there are better ways to dispose, not better, but more practical ways to dispose a list. But this one, once again, illustrates a nice way to do it using recursion. All right, so to recap, we showed how to build a list, how to process it sequentially, how to process it recursively. And the last thing that I want to say, which is very important in this course, is to once again open the hood and see how this list is stored in memory. The client view, or the high-level view of the list, is this, and yet within the memory it is stored using this example here. It starts with, say, v, c'est la v, and v contains the address 5267. If we look at this address, we'll find the value 2 and a pointer to 14017. If we go there, we find the number 3 and a pointer to 3108. We go there, we find 5 and null. So that's how the list is stored in memory. We don't have control over these addresses. They are completely arbitrary. I made them up. And in fact, that's what happens in practice. When you say new, the constructor is going to cause this object to be created somewhere in memory. We don't care where. All we want is a pointer to the base address. And therefore, practically, the list is going to be dispersed, all over the memory. And that's perfectly okay, because the memory is direct access, and that's fine. So who makes this magic happen? Obviously, there's some magician here that knows how to take this abstraction and map it on the sequential RAM. And here's the secret. If you are content to think about programming from a high-level perspective only, then the simple answer is the constructor takes care of it, somehow. But if you are interested to go below the surface, as obviously we do in this course, then you should know that when the compiler translates the constructor's code that the high-level programmer wrote, the compiler is going to inject into the code stream calls to the operating system that, and these calls are going to invoke routines that know how to find available memory for the new object and assign it to this object. And in the next modules of this course, when we build the compiler and the operating system, you will be very pleased to see how all of this capability is going to be implemented in a very elegant and effective way. All right, so the next thing that we'll do in this module is describe the Jack language specification. Up until now, we just showed example of Jack programming. Now we'll define the language officially, and you'll be able to start using it and write programs in Jack.